to you. So we call this Nature Wants Us to Be Fat, Part 1. So the very first thing to be aware of is that, everyone knows we're in an epidemic of obesity and diabetes. But, it really began around 1900. And about that time, about 1 in 30 people were overweight or obese. And approximately 1 in 50,000 were diabetic. Today, it's like 12% are diabetic, like 30% are obese. Hypertension now affects 30% of our population. Chronic kidney disease is very common. Heart disease is the number one cause of death. I mean, it was rare back in 1900 for coronary artery disease. So we've seen a dramatic increase in these diseases. And while we've developed great ways to manage and treat these diseases and surgeries and stents and thrombolytic therapies and all these different types of treatment, it would be a lot better if we could figure out the cause so that we could actually prevent these diseases from happening. Well, one of the things we do know is that people with obesity often have a constellation of findings. They don't just have being overweight. They'll be pre-diabetic, where their blood glucose will be slightly elevated. They'll have mildly elevated blood pressure. They'll have increased fats, not just in their tissues, what we call adipose tissue, but also in their blood and their liver and other sites. They'll have some evidence of systemic inflammation. And another particularly interesting finding is that many of them will have a high uric acid in their blood. And uric acid is present in everybody. It's kind of a breakdown product from nucleic acids and DNA. And we make this stuff and then we excrete it. But it seems to be high in patients with obesity and metabolic syndrome. And it can cause a disease called gout, where you get this arthritis that affects typically the big toe. Anyway, so obesity, metabolic syndrome is the name for this constellation of signs. And the bad part is that if you're pre-diabetic, it increases your risk to become diabetic. If you have elevated blood pressure, it increases your risk to become hypertensive. If you're overweight, it increases your risk to become obese, et cetera, et cetera. You have mild kidney disease early on, and then you can develop kidney disease as you get older. And all these add up to increased risk for stroke and heart disease and so forth. So it's one kind of related problem. Some people present more with a fatty liver, others present more with the diabetes, but it's all part of one syndrome. So that means that there could be a central mechanism driving it all. Now, a lot of people think that what's driving it all is being overweight and obese, and that it's really simple, that we're eating the wrong foods, we're watching too much TV, inactivity leads to weight gain, and so that, one of the most classic hypotheses was presented by Elliot Jocelyn way back in the 1930s. And he said, it's sort of obvious. People are eating too much, they're exercising too little. This we learned about in physics. It's called the law of thermodynamics. Too much in, too little out, and you have to store the extra as fat. And so if we're eating too many calories and we're exercising too little, that's it. And you know what you should do? Exercise. You know what you should do? Reduce your food intake. It should be easy, but it isn't easy. And you and I both know it. You can lose weight by exercising and eating less, but there's something that seems to drive us to become obese again. When we were young and 18 and 20 years old, it seemed like for many of us that we were invincible. We could eat anything we want. We could do anything we wanted to do. Didn't matter. We weren't going to gain weight, but something changed. We call it our metabolism has changed. We're now, as we get older, suddenly it's easier to gain weight. But why is that? What's driving it? What's activating this biologic process that causes weight gain? So we were very interested in this, and we approached it multiple ways. I wanted to not just do classic research, but I reviewed history and archaeology, and I wanted to think outside the box. And I began to realize that maybe one way to think about this is not to think about obesity as a disease or as a condition that's bad, because some animals in the wild actually intentionally become obese. It's like something good. And if we could understand what it was, how it was being good, and what was driving it, and how animals turn it on to become obese, then it could be a solution. It could be an answer for why we're becoming obese. So the first thing to know is that animals actually regulate their weight really well. If they eat too much one day, they'll eat less the next. They keep their weight stable. If you overfeed them or if you fast them, their weights will change, but then when you stop that, they'll go right back to the weight, and not just their normal weight for that time of the year. It's really interesting. So weight is normally tightly regulated, normally. But there are some animals that will intentionally gain weight. And so they'll maintain their normal weight 9 months a year, and then, a few months before winter, suddenly they start preparing for winter, and they start eating a lot, like the bear, the hibernating ground squirrel. Suddenly they go from being tightly regulated to one where they're dramatically eating more, gaining fat, and so forth. And the same thing's true for birds that have to fly long distances or birds that have to nest for several months. They'll put on all this weight. And the weight, the fat, actually provides a caloric source. It's a type of calorie they can use when there's no food around. Because when they break down the fat, it's basically a type of stored energy, and they will release energy that they can use. And everything's about energy. Well, it's not just the calories and the energy that's produced. When you burn fat, you also produce water. And for some animals in the world, they're really, water is kind of a critical thing. And so if you like living in the desert, it's good to have a little extra fat on board, because when you burn the fat, you produce water. That's why the camel has a hump on its back. That's why some of these fat-tailed animals, like the fat-tailed lemur, when it hibernates, they call it estivation in the summer. But when they hibernate, they're burning the fat in their tail to provide them water to get through the dry season. And whales, they don't drink seawater. That's too salty for them. So they get their water from food, and some of it from the fat they have, and they are fat. All right. So in the wild, fat is a good thing. Fat can keep you alive. Fat is a mechanism to help you survive when there's no food and no water. But it isn't, when these animals become fat, it isn't just they become fat. They actually develop all those features of metabolic syndrome that we were talking about that we get. They become insulin resistant. They raise their blood pressure. They increase the fat in their liver. They increase the fat in their blood. They do all these different things that we see in people with metabolic syndrome. It's like an orchestra. It isn't just about one guy. I'm going to increase the fat in you. It's another guy saying, I'm going to make you insulin resistant. I'm going to raise your blood pressure. I'm going to give you some systemic inflammation. It's a survival response. It's an orchestrated response, which suggests that there may be one driving cause. Now you may say, well, how is insulin resistance part of a survival response? But the way it is that normally a lot of our tissues like glucose. Glucose is the main carbohydrate in our blood that we use as a fuel. So yeah, we use fat as a fuel, but in terms of carbohydrates, we use glucose as our primary go-to fuel. And it's used a lot by the brain. It's used in tissues like the muscle. But interestingly, it requires a hormone of insulin to move the glucose from the blood into the muscle. But there's less need for insulin in the brain. The brain, a lot of the brain can use glucose without insulin. So when you become insulin resistant, there's less glucose going to the muscle, so there's more glucose that can go to the brain. Basically, it allows the glucose to build up in the blood so that there's more for the brain. And that is a good thing if there's a food shortage. You want to preserve the glucose you have for the organs that count. And when it comes to survival, the brain is the king, okay? It isn't the heart or the muscle or the kidneys. I'm a kidney doc, but it's not none of those. It's the brain. You've got to be able to think if you're going to survive. So what triggers this survival response? Well, for sure, we've already known this for some time, that many animals will use fruit as a mechanism to start increasing their fat. And this is known. The bear, for example, can eat 10,000 grapes in a day in the fall, and it goes from kind of tightly regulating its weight to gaining 8 to 10 pounds a day. Birds will switch from insects more towards fruit in the fall. They use the fruit to increase their fat. There's even fish that eat fruit fallen from trees into the river, like in the Amazon when it floods, and they use that fruit to build up their fat stores so that they can make it through when the river contracts and there's less food around. And there's primates like the orangutan loves fruit and will sit in a tree and eat fruit all day long. And so it's eating huge amounts of fruit, getting a lot of this. So what are they getting? Well, you have to know that the main nutrient in fruit is fructose, and that's a sugar. It's sort of like glucose. It's distinct from glucose. It's much sweeter. In fact, if you take glucose and you give it to a person that's just very lightly sweet, people tend to like it, but they don't love it. And so what we discovered is that when fructose and glucose are together, then suddenly you have something that people love. And that was the discovery of sugar, table sugar, sucrose, which is a fructose and glucose molecule bound together. And then in the 70s, they discovered that they could make a sweetener from corn called high fructose corn syrup, which is a mixture of fructose and glucose. And then, of course, there's what we call those high carb foods like potatoes and rice, and they have starch, they don't have sugar, so they don't have fructose in them. But what happens is these foods have a lot of starch and they break down to glucose. And as we'll learn in lecture 2, unfortunately, these foods can also have a role in causing obesity. And it's going to be through the same pathway. But we're going to hold off on that for now and just move on with, now that we know that the fruits that these animals eat contains fructose. So the question was, could fructose be a nutrient that activates the switch that makes you want to gain fat? Could that be the driver of the biologic switch? So we took lab mice, and we put fructose in the drinking water. And by God, they loved the drinking water. They were drinking a lot. For the first couple of weeks, they held their weight stable because they were still regulating their weight. And then something changed, and they suddenly lost their control of appetite, and they started eating more and more. They exercised less and less. They became less active, especially when they're not, what we call resting activity. Metabolism dropped. And what happened was they became fat. So the equation was the same. They're eating too much, they're exercising too little, but it's being driven not by a desire. It's not being driven by behaviors. It's actually a special food. You give them this food, and suddenly they start eating more. So what is it about the food? Is it the taste, for example, or is it the metabolism? What is it that makes fructose cause this syndrome? And so what we did was we took mice that couldn't taste. Let's just see if it's taste. And so we took mice that had lost their taste because of a genetic manipulation. And then we offered them fructose or water. And normally if they have 2 bottles to choose from and they both contain water, they'll take the water evenly. They'll take about half of it from this bottle and half from that bottle. And you can switch the bottles and, nothing happens. But if you give them sugar water or fructose water and drinking water, normally animals will take about 80% of their fluid from the sugar and 20% from the drinking water. So they'll drink some sugar water, but they'll drink about 4 times more. And, if they can't taste, you would think that they wouldn't care. But guess what? A mouse that can't taste can still figure out where the sugar is, and it will take the sugar water just like it will a normal mouse, except that overall it takes less sugar, but the preference is the same. It still takes about 4 times if they have their choice, they're going to go to the sugar water 4 times more, even if the total amount of sugar they eat will be less. So the taste is there to encourage you to find the foods that are sweet, and they probably encourage a little bit more intake, but it's actually doesn't affect your desire for it. So the desire for sugar water is independent of taste. And they will still get fat. If you give them sugar water, they still get fat even though they can't taste it. Amazing. Now, if you block their ability to metabolize fructose, and we can do that by blocking the enzyme, and I call that enzyme KHK, and when you block it, we call it a knockout. So these mice can't metabolize fructose. Well, when you can't metabolize fructose, guess what? They don't care for fructose anymore. And they don't get obese even when you force them to eat the same amount. So there's something about fructose that's making them want to, they crave it even though they can't taste it. And they will get fat from it even if they can't taste it. And it's something to do with the metabolism of fructose. So let's figure out how that works. How does fructose work? Well, and is it all from calories? Because I'm sure you guys have heard, hey, it isn't just calories. I mean, if it were just calories, then why would a low-carb diet be so much better than a low-fat diet? And we know that low-carb diets really are better, right? That's why you're watching this show, because low-carb diets do work. So the question is, what is it? Is it more? It's got to be more than calories. Well, it is more than calories, but let's do this scientifically. Let's try to figure it out. So one way to figure it out is you take animals and you feed them the exact same number of calories. You can get sugar and you can get fat, or you can, fat in your diet, or you can get fructose and we're going to not give you fructose. So we take this all these rats, and we can say, you guys are all going to eat the same amount. But of course, we can't really tell them, you're going to eat only X amount. So we have to serve them the same amount of food. But what happens is, to do this right, if you serve them all the same amount of food, there's always one guy that eats less than the others, right? So if you really want to do it right, you have to feed them all the same amount as the guy that gets the least. So basically, all the animals end up eating the same amount as the guy who eats the least. Now, when we did this experiment, we did this multiple times. But one time we did the experiment where one of the poor guys had cancer, so he was eating much less. So that experiment's really interesting because they're all eating less than they normally eat. So guess what? If you're going to put you on a diet, but one group gets high sugar or fructose and sugar, and the other group doesn't get a fructose-contained sugar, what do you think happens? Well, when you can't eat all that extra food, even though you're hungry, you're not going to gain as much weight because you're just not eating as much food. But you'll still gain a little weight because you're reducing your metabolism as well. So when you activate this switch, you eat more, but you have your resting energy metabolism goes down. And so, boom, the animals that got this sugar, which here's sucrose, which is glucose and fructose, they actually gained a little weight even though they're on a diet. So they were able to conserve their energy enough so that they actually gained weight even though they were eating less than they normally eat. The control animals, of course, lost weight. But it was just very small amounts. So, one could argue that it wasn't really significant. But what was significant was, even though the differences in weight are almost zero or very minor, we're seeing huge differences in metabolism in the body. So the animals that got sugar got fatty liver, they got diabetic, they developed hypertensive. It was a very significant issues. And so even when calories are the same, there's something special about fructose. It isn't just making you eat more. It is poisoning your system where you're developing diabetes and fatty liver and all those things. And you can do it even when you're on a diet if you're eating a high sugar diet. So what is it about, how does that work? What's the chemistry? Now Forgive me, we're going to go 2 or 3 slides deep into chemistry, but it's not going to be super deep. But here it is. When you eat fructose, it's like all nutrients. You use it to make energy. You eat calories to make energy. And we make energy that is either immediate energy, which is the ATP that makes me want to be able to do everything you want, or we store it as energy, which is what we call as fat. And this is, and normal calories do this. But fructose is unique because what it does is it has a side path where it generates uric acid inside the cell. And I call it a non-caloric pathway because you can activate that pathway even without when you block the caloric pathway. And yet when you do that, you activate the switch. So the switch turns out to be associated with this non-caloric pathway unique to fructose. And what that does is it generates uric acid. Inside the cell, the uric acid goes up in the blood, and it activates the switch. And if you lower uric acid in these animals, and that's all you do, you can actually affect the ability to raise blood pressure, to increase their weight, increase their triglycerides. So there's an association, there's a relationship where uric acid being produced inside the cell is triggering this switch. And how does it do it? Well, here's the complicated slide. Basically what it does is it helps reset the energy in the cell to a lower energy. So remember, energy is ATP, and then there's a stored energy, which is fat. So if the way fructose works is it makes the energy level or the ATP level low because it tends to shunt more of the calories to fat. So when the ATP levels go low, it sort of activates an alarm. It makes you want to eat more, forage for food, and activate the switch. And the actual way it works is like a series of really cool reactions. So when fructose is initially metabolizes, it consumes some of the ATP, and all foods consume energy when they're being made, but fructose is unique because it consumes it so rapidly that there's a fall of energy in the cell. Normally energy doesn't fall in the cell, it's just maintained at a very high level. But fructose triggers this drop in energy that then activates an enzyme that removes the AMP. AMP is what's used to reconstitute ATP. So when you make AMP, then you can make it back to ATP, but this guy is like the giant sweeper, and it sweeps away the AMP to make uric acid, and then the uric acid goes and stuns the energy factories where ATP is made, reducing the ATP production by blocking what we call the Krebs cycle and fatty acid oxidation and all these things you don't really want to hear about. And then it blocks the regeneration of ATP in a low energy state by blocking this great enzyme called AMP kinase. And the result is ATP levels fall. Alarm signal, it makes the animal feel like it doesn't have enough food because the energy's down, but actually it does. It's just stored fat, and the stored fat can't be released into regular fat because it's blocking that. So fructose blocks the ability of the fat to be broken down to generate energy. So the animal feels that it's in a low energy state. It feels like it's starving. And guess what it wants to do? Eat. It wants to eat. It wants to increase its fat stores. It's perfect. It's a way to increase fat in an animal that already has fat because it tricks the system into thinking that you're in a low energy state, and it puts you in a low energy state. And what does that mean? Well, again, the uric acid goes into these energy factories called mitochondria, and it blocks the production of ATP, and that leads to the stimulation of fat as a stored energy, and the dropped ATP leads to fatigue and being tired. And now you've got it. You're slower, so you're spending less energy. You're fatter. You're putting weight on. You're hungry. It's making you fat and tired. Not great, but it's really good if you got to survive a period of time where there's no food around. All right, so that's how the pathway works. But there's another side to it. And the other side to it is that we, humans, you and me, are much more sensitive to fructose than most animals, and that's because of something that went wrong a long time ago. So this pathway was meant to save our lives, and guess what? It did. But the consequences of that is it made us more sensitive to sugar, and here's how it worked. So there's a famous scientist named James Neal back in the 1950s. He came up with this idea when he was studying natives in different environments. He said, maybe the reason obesity and diabetes are happening today is because we inherited or got mutations that affected our ability to survive in our past when things were really bad. So if there was a famine, maybe we had a mutation that allowed us to help survive the famine, but it's increasing our risk for obesity today now that there's a lot of food. And this thing got called the thrifty gene hypothesis. It was really this great idea that maybe the reason we're becoming obese and diabetic is because of something that happened in our past. Well, I told you the importance of uric acid in driving this whole process. And it's interesting, humans have much higher uric acids than almost all other mammals. So why is it that we have these high uric acids? And guess what? It was from a mutation that occurred millions of years ago that affected our ability to degrade uric acid. So normally uric acid is like produced when you eat foods, you can make uric acid. It's also produced when energy turns around like ATP, well, like as we talked. And we always have some uric acid in our blood. Normally there's an enzyme. Most animals have an enzyme that degrades it. We lost that enzyme. So when we make it, it's harder to get to lower it because we can't break it down. So we have to excrete it through our kidneys, our gut, and as a result, we can't do that as well as just breaking it down. And so we end up with higher uric acid levels than most other animals. Now, why would we want that? So, and was it an advantage? Well, when we look at the history of this mutation, we see that it actually occurred millions of years ago, that it didn't just affect us, it affected all the apes, the great apes, the lesser apes, and humans. So so it seemed to have hit an ancestor, and it happened millions of years ago. And the consequence of a high uric acid, the one that we best know, is a disease called gout, because when our uric acid gets really high, it's not very soluble, and it crystallizes, and it loves to crystallize in joints, causes this terrible, painful joint disease called gout, and it often hits the toe, and these crystals deposit and they activate inflammation, and it's hard to walk, and it hurts like for several weeks until you finally get the pain under control and the inflammation under control. And so why would we have a mutation that increases our risk for gout? And what was happening to our ancestors millions of years ago? So I love history. So I went back, started looking at what happened way back then. And the first apes appeared in Africa around 20 million years ago. They were larger animals than the other monkeys and primates, and these guys had big heads. They were tailless. They lived in the trees, and they ate mainly fruit. They loved fruit, and so they were eating a high fructose diet. So they were eating a lot of fructose, and they were doing pretty well. They actually were probably not eating it. They had this mutation. They had uricase way back then, and so they were doing very well. And then what happened was we had a change in temperature. CO2 levels fell, and we had global cooling, not global warming. And as the CO2 levels fell in the atmosphere, got cooler, polar ice caps formed, the sea levels fell. And Africa, which had been pretty much separated from Europe, suddenly, as the sea levels fell, there were land bridges, and the primates and apes and other animals entered Europe. Now, initially, when the apes arrived to Europe, there were plenty of fruit trees, and they were able to live just the same way they did in Africa. But as it continued to cool, the trees became a little bit more sparse and turned into woodlands instead of rainforests, and they became more deciduous, and there became more open areas and savannas, and these apes which had been living in the trees, they had to come out of the trees, they had to forage more for food, they couldn't find fruit all year long, and especially during the cooler months, there was less fruit available. And so they started to starve, and you can see signs of starvation by looking at their teeth. And when an animal's starving, they can't put the enamel down as well, so they get these rings of poor growth of enamel. And these rings kind of look like tree rings, and they're a sign of seasonal starvation. These animals were starving, especially during the cooler months when there wasn't fruit available. And when that happened, these poor guys started to become extinct, and they retreated to little colonies. And then around 8 or 10 million years ago, there were no more apes in Europe. But in Africa, where it was wetter and warmer, the fruit trees were present all year round. So there wasn't really as much of a survival problem there. So the forest contracted, but the apes were able to survive on their normal foods. But it's interesting, the fossil record suggests that our species, and also the great apes and the lesser apes, were all seem to be derived by the fossil record from the apes in Europe, not from the apes in Africa. In fact, there's this thought that some of the European apes must have migrated back to Africa to be the ancestors of humans and great apes, and others may have migrated to Southeast Asia to be like the ancestor of the orangutan. And so I thought this was really interesting, and I flew to London to meet with Dr. Peter Andrews, a famous anthropologist who studies these Miocene apes, these apes from this period 10 to 15 million years ago. And I told him our hypothesis that that this mutation had occurred that affected uric acid, that uric acid is produced when you eat fructose, which is what these animals were doing, and how this mutation could potentially allow an animal to generate more fat from the same amount of fruit, and that might allow it to store more fat in a situation when there was less fruit available, that would allow them to survive winter, and then and from that be able to survive. So he liked the idea. We published the hypothesis, but of course we needed data. And one of the key experiments was done by our collaborator, Gabi Sanchez-Lozada. And what she did was she said, okay, laboratory rats have uricase, and it's true you have to give them a large amount of fructose to get them to be fat. What if I gave them a small amount of fructose but inhibited their uricase? Could I still make them fat? So she put them on very small amounts of soft drinks, and then she inhibited uricase on top of it, with or without. And what she found was that when she inhibited uricase, the uric acid levels were higher, not surprisingly, but so was the prediabetes, the blood pressure, the body weight, the increase in triglycerides, the liver fat. Everything was enhanced. It was exactly true. We also even resurrected the extinct gene. We resurrected the extinct uricase gene and found that when we did so, that we could that it could block the ability for fructose to make fat, and that when we mutated it like we did, that we could increase the fat response. There's even some data that uric acid can be a survival factor for starving animals. And way back in the 80s, people found that if they gave uric acid injections to starving animals, that it was similar to giving glucose, and that it could help animals survive, especially if they had troubles breaking down fat. So what we know is that this uricase mutation was probably there to help us survive when there wasn't a lot of fructose around, and it enhanced our ability to make fat and to activate this survival pathway that included foraging and blood pressure and brain fuel. These were all things that this mutation allowed us to do. So it was a good guy. But guess what? Today, it's not a good guy. And the reason is because of what's happened since that time 15 million years ago. So When that mutation occurred, it only raised the uric acid a little bit. And the way we know that is because if we go and we study animals in the wild like the orangutan or the chimpanzee that had the mutation like us, their uric acid levels are only around 2 or 3. And likewise, I was able to get blood samples from the Yanomami Indians from actually the same expedition that James Neal went on. And we were able to show that the uric acid levels in the Yanomami Indians was also around 2 or 3. So when the mutation occurred, the uric acid levels went up only a little bit to like the 2 or 3 range. And that was enough to prevent us from starving, but not enough to make us fat. But then a new source of fructose came, and that new source came from sugar. And the discovery of sugarcane in the Ganges River Valley around 500 BC led to suddenly a new sweetener that had a lot of fructose and that people liked. And pretty soon, diabetes and obesity were being reported even from that area. And then the sugar got brought from India into Persia and China and Egypt. And we start seeing reports of obesity and diabetes there around 500 AD, for example. And then it's brought in through Venice during the Middle Ages. And suddenly we start seeing obesity and diabetes among the people who could afford the sugar. And it was very expensive. So it was really just the royalty and the wealthy. And in those days, if you were poor, you were not at risk for obesity. It was the wealthy who were, and it was the wealthy who could afford sugar. But then as sugar production increased, both with the sugar plantations in America, with the advent of sugar beets, and then in the 1970s with the production of high fructose corn syrup from corn, suddenly these sweeteners that have fructose in it are everywhere, and they're being put in processed foods, and they're being put in. And today, about 15% of our diet contains sugar. And some people, it's 25% of our diet is sugars and added sugars. That's a huge amount of sugars. In 1700, we were only eating 4% or 4 pounds of sugar a year, and today we're eating 140, 150 pounds of sugar a year. All right, and guess what? Now you got a lot of fructose, and we're sensitive to fructose, so obesity and diabetes rates are soaring, and they parallel the rise in sugar. Uric acid levels are soaring, they're going up. They were around only 3 to 4 milligrams, remember, following the mutation, but then with the advent of sugar and foods and beer and other things that can raise uric acid, the uric acid levels continue to increase in our society. And today, about 20 million people in the U.S. have uric acid levels of 7 or higher, and that's the level where you start seeing gout. And so it's a real problem. And when you have gout, guess what? You see a lot of obesity, you see a lot of diabetes, you see a lot of kidney disease, you see a lot of metabolic syndrome. Gout is the greatest risk factor for all these diseases. They're all part of one syndrome. And now, if you look at uric acid levels and the frequency of obesity, look, you have a uric acid of 10, you have a huge chance of having obesity or diabetes. It's amazing, and you can see how it isn't just the mutation, it's the mutation plus a food that's driving the obesity epidemic. And it's true for kidney disease, and it's true for hypertension. And the higher the uric acid, the greater the risk. And even in people who have a high uric acid, who have no other risk factors, no obesity, no diabetes, no elevated triglycerides, those people, if you have a high uric acid, you're at increased risk. And this slide shows that you have an increased risk for obesity and hypertension and kidney disease and diabetes and fatty liver. It's bad news. It even predicts, of course, heart disease, because when it's predicting all these different diseases, it's going to also predict. And gout, in particular, is associated with a higher risk for these diseases. Well, what about fruit? I mean, I understand that fructose is causing the obesity epidemic, but we've been told fruits are good. Is fruit a culprit? Well, the vast majority of fructose you're getting is from sugar. It's from added sugars. Fruit makes up just a small amount. And most fruits, when we eat them, we're only eating a small amount, and the fruit has only a limited amount of fructose when we're eating an individual fruit. If you're a bear and you're eating 10,000 berries, you're going to get fat. Okay, if you had a bowl of grapes on the couch, you're going to get fat. It adds up. But if an individual fruit is not going to do it, it's got fiber, it's got vitamin C, it's got potassium, it's got a lot of things that block the effects of fructose. And so you have to eat a fair amount, especially ripe fruit, and we tend to like tart fruit. And what's more, the intestine removes about the first 4 or 5 grams of fructose. So that really helps out a lot too. So natural fruits are good. So in summary, there is a biologic switch. Obesity is driven by a switch. That switch is fructose. And how the fructose works is it drops the energy in the cell, creating a false sense of starvation. And the major sources of fructose are sugar and high fructose corn syrup. They make up the most. And it's really liquid sugar that's the worst. Humans are more sensitive to fructose because they had a mutation in uricase 15 million years ago. So we are more sensitive to sugar. And we're eating a lot of it. Some people make it 25% of their diet. And this is why we're developing obesity, diabetes, metabolic syndrome, and all these diseases. Now, I'm going to tell you a very bad surprise in the next lecture about how the body can also make fructose and how certain foods that don't contain sugar can still cause obesity. So stay tuned. Thank you very much. I want to do special thanks to my collaborators. And of course, all of this information is in my book, Nature Wants Us to Be Fat. Thank you very much.